Okay, we're working on the average and standard deviation worksheet. So here you have a list of composite ACT scores for students in the class, and you need to use that information to answer these 4 questions. What is the median, and what does the median tell us? What is the mean, and what does the mean tell us? So I'm going to pause the video. You guys do the calculations, then I'm going to turn the video back on. Okay, welcome back. How did you calculate the median? Oh, we have to reorder the numbers and then find the middle number. And when you did that, there wasn't a middle number. What were the 2 middle numbers? 21 and 22. So the average of those 2 is going to be 21.5. So the median of this data set is 21.5. Any questions there? Okay. What does the median tell us? And I wish statisticians would have chosen a different word, because I want to say, what does the median mean? But mean is also average. So what good is the median? No idea? This one you probably actually know. It's not tricky like the average is. It's the middle number. So if I said the middle number is 21.5, what does that tell me about the data set? You can be more specific than that. Not just it goes above and below. There are an equal amount above and below. So half of the scores are bigger than 21.5, and half of the scores are smaller than 21.5. That's what the median tells us. Okay? What is the class mean? 23.3 repeating. So that's the average. What does the average tell us? If all of the points were distributed evenly, everybody would get 23.3. Okay? Now, a lot of times we reduce an entire data set down to the average. And they said, well, how did kids do on the test? Well, the average was 23.3. Does that give a very good picture of what actually happened? No, it's not. But that's what we do. Did anybody score 23.3? No, that's not a possible ACT score. Okay. All right, next problem. Suppose the Utah High School Activities Association wants to see how accurately the lines on high school footballs are drawn. I need to fix that. Wow. It's almost like I wrote this today. By measuring, so it should say by measuring the distance from goal line to goal line. The true distance should be 300 feet. When they take a laser measuring device to all fields in one region and measure, they record how far away from 300 feet each measurement is. Fields that are too long are given positive values, and fields that are too short are given negative values. Here are the results. So they come and measure Emory High, and they record 3. What does that mean? Emory High's football field was 3 feet longer than it was supposed to be. Okay, the next field they measure is -2. What does that mean? It was 2 feet short. Okay, and that just takes less room, right? We don't need to say 303, 298, 299. We're just recording the differences. Okay, I want you to go through and answer these 6 questions using that data set. And I'll pause it and come back when you're done. All right, what did you get for the median? -0.5. Okay, -1/2. So what does the median tell us? Half the fields are above half of a foot short, and half of the fields are below half of a foot short. So how useful is the median in this case? Not very useful at all. Okay. What is the mean? 0.1. Okay, so what does that tell us? If you ran over to Carbon and you cut up some of their turf and you brought it over and you planted it in ours, and you did that so that all of the fields were the same length, then all of the fields would be 1.2 inches long, right? 1% or 10% of 12 inches long. Okay, so how useful is the mean in this case? Totally useless. Totally useless. Right? So, we're going to do something a little bit different to calculate the average. Okay? So in describing a data set that has both negative and positive numbers, it often makes more sense to drop the negatives and take the mean. So recalculate the mean using this method. So I'm going to do 3 plus 2 plus 1 plus 2 plus 5 plus 4 plus 1 plus 1 plus 2. And then how many were there? And I get 2.1 feet. Okay. What does that tell us? It is not our standard deviation. But what does that number represent? 2.1 feet. So it has absolute value in there, true? From 300 feet. So this number is the average distance from 0, right? That number is way more useful than 0.1. If you went out and measured the fields and you reported and said, the average distance that we were incorrect was 0.1 feet. That is not representative at all, right? How many of those numbers were close to 0.1? 0 was close to it, but that was a field that was exactly the right length. So if you wanted to use the average to determine how accurate the fields are, 0.1 is a horrible number. But if you get rid of the negatives and then take the average, you get 2.1, which means on average the fields were within 2.1 feet of being correct, whether it was too big or too small. Okay? All right. What is the name of this value? It is the root, or sorry, oh my gosh. I don't ever use this number, so I forget it. The average deviation from the mean. That number is called the average deviation from the mean. And number 13, what does that value tell us? On average, the fields were 2.1 feet wrong in one direction or the other. Okay. Now, hold on, I'll let you finish. That number is very, very useful. And yet, nobody ever uses it. In fact, I forgot its name because this is the last time you're going to hear it this year. Okay? But we do want to know how far numbers are from 0. And when we did this calculation, we did the absolute value, added them together, and then divided by the total number, right? What is another calculation we can do that will get rid of negatives? Square things, okay? So we can calculate what is called the root mean squared. And it's pretty similar to the absolute value. In fact, your calculator does not know what the absolute value means. Like, absolute value is not an operation. It's something that we can do, but the calculator doesn't know how to do it. So here's how your calculator figures out how to do absolute value. Well, all your calculator can really do is addition. That's it. It can do addition, and then if you add a negative number, it's known as subtraction. And if you do the same addition over and over, then it's multiplication. If you do the same subtraction over and over, it's called division. And if you do the same multiplication over and over, it's an exponent, right? So all your calculator can do is add. So how do we get rid of negatives if all we can do is add? Well, adding leads to multiplication, and multiplication leads to exponents. So if I wanted the absolute value of 2, what your calculator does is 2 squared, and then it takes the square root. So if I had -3 and I wanted the absolute value of it, your calculator is just going to do the square of -3, which gets rid of the negative, and then it takes the square root to undo the square. And that really is just addition, dressed up in a really complicated way. So here is the formula for the root mean squared. Okay? You take your x value and you square it. That gets rid of the negative. And you do that for all of the x's. However many it takes. Okay? And then you take the average. So you divide by however many are in the list. Right? And where do we stop? We stop at x sub n. So this is x sub 1, x sub 2, x sub 3, all the way to x sub n. But my answer is going to be way too big. How come? Because there's a squared in there. And then we take the square root. Now, when we do this, we're not going to get the same number. So everybody calculate the root mean squared of those values. So of this. So we're going to take 9, 4, 1, 0, 4, 25, 16, 1, 1, and 4. And we're going to add all those together. We're going to divide by 10. And then in the end, we have to take the square root.
What numbers again?
So the numbers in questions 5 through 10. So those that oh, you can't see my screen. I'm sorry, Byron. If my screen's not up there, just say, hey, dummy, put your screen up.
Will do.
Okay. So these numbers, so here's the calculation right there. Sorry about that. What did you get? 2.55. So the, again, I forgot its name, the mean absolute, oh shoot, I meant mean deviation. See? Whatever. Is it Friday? It's Friday. So this one is the mean, I'm sorry guys, absolute deviation. Deviation. And don't worry about it. It's not a big deal because we're not going to use it. In fact, every year I have to look up its name because nobody uses it. So the answer to 12 is the mean absolute deviation. And we got 2.1, right? So now we computed what is called the root mean squared. And the root mean squared was created using this squaring technique. And when we get the squaring technique, we will always get a number that is slightly larger than the mean absolute deviation. Why is that? Because when you square the numbers and then you take the average before you take the square root, it's sort of like looking at the hypothesis of a triangle compared to the side lengths. Right? The sides of a right triangle are always going to be smaller than the hypotenuse. And essentially, we just took a really, really, really big a multivariable version of the Pythagorean theorem. Okay, so the root mean squared is always going to be larger than the mean absolute deviation. But we will use the root mean squared all the time, even though it's a little bit bigger, because it turns out that the amount bigger that it is perfectly suited for what we want to do. And the probabilities we're going to be computing match up perfectly when we do the root mean squared. If you use the mean absolute deviation, you're always going to be a little bit off. So that is what we want. And next question is, come on. What does this value tell us? And this is sort of like the average distance from 0. Okay? So it's going to be slightly larger. This is what you'll write down. Slightly larger than the average distance from 0. All right. Next page. Okay. A class takes a test and gets the following scores. So I'll work this one with you. Let's find the average. I will race you. I'm going to lose because I'm pushing the wrong button. What'd you get? So the average is 83. Okay. Now, calculate the difference of each score from the mean. So how does 78 compare to 83? It's -5. 85, 2. So then we'll have 8, 1, 0, 10. 9, -11, -23, 3, and 6. So those are our differences. Now calculate the root mean squared of the differences. So we're going to square every single one of these, and then we'll divide it by 11, and then we take the square root. All right, so 5 squared. I got 9.4. Is that what you guys got? Okay, so this is 9.4. And I said 4 and I wrote 5. 9.4. What does 9.4 tell us? Yeah. So the average distance from the average is going to be somewhere slightly smaller than 9.4, maybe like 9, I don't know. And for the purposes of this class, we're just going to call this the average distance from the average, even though it's not. So this number tells us that the scores in the class, on average, are 9.4 away from 83. Does that make sense? Because this is hugely important. We are no longer comparing this to 0. When you take the root mean squared, you are finding the average distance from 0. But now we are finding the average distance from 83, which is basically the root mean squared of the differences. So what is the name of the number that tells us the average distance from the average? That is the standard deviation. So number 20 is called the standard deviation. And the standard deviation is the most important number in all of statistics. Okay, so let me help you understand what it's telling us. The standard deviation is a measure of spread. How spread out is the data? So if you took this test and all I told you was that the class average was 83 and then we went home for the weekend, you're not going to be very satisfied with that, right? You might think I did well on the test, but knowing just the average doesn't tell me anything other than we lumped all the class together, and if we shared our points, everybody would get 83 points. But if I told you that the average was 83 and the standard deviation was 9.4, and then we went home for the weekend, that gives you a much better sense of where your score is according to how well you think you did. Okay? So here is a rule of thumb. 68% of all scores are within plus or minus 1 standard deviation. So if you take the average and you go up 1 standard deviation and you go down 1 standard deviation, 68% of all scores are in that window. So if I draw a bell curve and I put 68 here, right here is a special point called an inflection point. If you take in calculus, you know what an inflection is, what an inflection point is. That's where the graph turns from concave down to concave up. So can you see that this part of the graph is sort of caving down, and this part of the graph is caving up? The point at which those switch is called an inflection point. And that inflection point is always exactly 1 standard deviation away. So if I go right 1 standard deviation and left 1 standard deviation, 68% of all people are in this window. Now that's only true of normal curves. Okay? If the curve is not normal, then this doesn't hold up. Okay? If we go out plus or minus 2 standard deviations, so we go this distance twice, I now capture 95% of all people. Okay? And if I go out 3 standard deviations, so out to here, I capture 99.7% of all people. So the standard deviation gives us a really good idea of the spread. And this rule that I've just written up there has a super fancy name. It's called the 68, 95, 99.7 rule. And we're going to be using this a lot. In fact, almost the entire class is going to be based off of that curve and those numbers. So how unusual is a score? Well, if you scored 63, is that an unusual score? Well, let's see where that is. It would be like right here. It's pretty average, right? 2/3 of the people are in that window, and this person is near the middle of all of those. What if your score was, say, 99? So this is about, so this is 77.4. No, not 70. 97.4. No, that's a 68. Holy cow. I was right the first time. So this is 77.4. We'll just say 78. 78. And so this would be 88. And this would be 98. How unusual is a score of 99? Very unusual. So that's how we measure whether something is common or uncommon. We look at the average and then we compare it using the standard deviation. And that is the essence of just about everything we're going to do in this class. All right. So your mission, should you choose to accept it, is to calculate the standard deviation of each of those data sets. So you need to find the average, you need to find the differences, you need to square the differences, take the average, and then take the square root. Okay? And there is an answer sheet on the back. Hopefully it's correct. All right. That's it. Get to work.